My name is Julie, and my topic for today is the anthropogenic phosphorus inputs into Georgian Bay. So Georgian Bay is part of Lake Huron, which is part of the Great Lakes. Georgian Bay is part of Lake Huron that's entirely within Ontario. And you can see to the north, there's a lot of trees, provincial parks. Algonquin is to the east. And then to the south, there's Barrie. If you go even more south, there's Toronto. So there's a lot more urban development to the south. And noticing there's a lot of shallow nearshore areas. There's a lot of little bays, harbors, and there's a huge fishing and recreational industry. Georgian Bay is known for its clear water and beaches. So historically, Georgian Bay has seen a lot of changes. And there's been three main events or series of events that have happened around the Georgian Bay shoreline. In about 1450 to 1650, the indigenous peoples of the area were practicing agriculture on the Penetanguishene Peninsula, and there was some land clearing that happened then. In about 1840, the European colonists had widespread land clearing for their agriculture, cutting down most of the forests and trees. And you can see in the lower left photo here in 1845, just noticing the lower end of Georgian Bay, how there was a lot more settlements coming up from Toronto towards the Georgian Bay region. And then in the 1970s, there was a boom of cottage developments close to the shoreline, especially around the southern end of Nottawasaga Bay. And so the second photo in the bottom right here just shows the areas between 1975 and 2014 and just how urban development has continued to happen. And the question is, what impact on Georgian Bay does this all have? One effect that increased human impact has on the Great Lakes is algae. So for example, Cladophora is a filamentous algae. It's basically stringy and it attaches itself onto surfaces like we can see in the photo here. So although it never reached nuisance levels in Georgian Bay, since Georgian Bay is not as close to huge urban centers like the lower Great Lakes, Ontario, Michigan, and Erie, it is present because it's a native species. It's a native species, but it increased in the mid-20th century to nuisance levels, affecting things like the beaches, water quality, and tourism. And it's what led to the Great Lakes Water Quality Agreement in 1972 between the US and Canada. Now, the Great Lakes Water Quality Agreement, when they did that, they discovered that the phosphorus inputs into the Great Lakes were causing cultural eutrophication. Now, eutrophication is a natural process that occurs with lakes, and it has to do with the trophic state of the lake. Cultural eutrophication is when this is artificially increased by human activity. So oligotrophic lakes are often colder, deeper, and have less primary production from producers like algae and macrophytes. Whereas eutrophic conditions have increased growth of these things related to increased nutrient input in the water. And phosphorus is the nutrient in question here, as it's the limiting factor for primary producers. So looking at the phosphorus cycle here, this image is described for Lake Simcoe, but the cycle is the same for other bodies of water like Georgian Bay. And we'll be looking at the top at the red arrows. Those are the phosphorus inputs from land into water, and we'll be ignoring the atmospheric part for now. So the main inputs are then from natural vegetation, and then from humans we have agriculture, and then urban septic and wastewater effluent. Another thing to notice here is that phosphorus is related to sedimentation. It can absorb onto surfaces of particles and soil matter and at the bottom of the lake sediments as seen here, and then it's known as particulate phosphorus. TP, total phosphorus, is the particulate and the dissolved combined. So when it's related to sedimentation like that, that means that when erosion increases into a body of water, so does the phosphorus input. A lot of this is facilitated by the movement of water in streams and runoff within a watershed. So did these past land use changes, conversion to agriculture, and increased human settlement along the water, did it cause any cultural eutrophication in the past? Now we can find this out by taking sediment cores and looking for fossilized parts of certain primary producers, such as diatoms, which are certain types of algae that can be fossilized, or polynomorph, which is a fossilized spore, essentially a pollen grain. And we can infer using the law of tolerance, figuring out what types of species were present and inferring what type of conditions were present then. So in this one study, cores were taken from several sites in Georgian Bay, on one reference site, Tatanac Bay, and the study site, which was Honey Harbor. And the reference site is known to be oligotrophic. It's far from human impact. It's quite protected, whereas Honey Harbor is surrounded by, not urban centers, but human settlements and agricultural lands. And it's known as a more mesotrophic area. And so they noticed a huge shift in the types of diatoms present in the 1970s associated with a higher trophic state towards more mesotrophic and eutrophic species. And just in the bottom of the chart there, the reference site has really low levels of phosphorus within the sediments, versus Honey Harbor has pretty high levels at over 100 micrograms per liter. In another study in Georgian Bay, they were looking at dinoflagellate cysts, another piece of fossilized algae, and they looked at two main species. One is Pyridinium wisconsinense, and the other is Pyridinium willi. And so wisconsinense prefers low levels of phosphorus, versus willi can tolerate high levels, so it has a broader range of tolerance. It can be found in pools and peat bogs, and it's known as more of the mesotrophic or eutrophic species. So what they saw when looking at the sediment cores is that there was a shift of the Pyridinium wisconsinense towards the willi species. So a shift from low phosphorus loving species towards the one that can tolerate high levels of it. And looking at the image in the bottom left, just underneath dinocysts, that represents the cores, and the stippled area along the top represents post-1840, when the European colonists began their widespread land clearing for their agriculture. And that's where we can see the decline in one species and the increase in the other. But this is actually also reversible. They noticed that after Awenda Park, which was created in 1975, the low phosphorus loving species started to increase again. Now shifting over to the current land use, we can see that to the west, the watershed has lots of forests, wetlands, and there's been some land conversion to agriculture. To the south, it's way more of an urban area. Forests are present but less common, and agriculture dominates. This image on the left shows the different routes that phosphorus can use to get into Georgian Bay. There's natural sources like forests and wetlands, and anthropogenic sources like agriculture, septic tanks, wastewater treatment plants, urban areas, and actually Lake Simcoe, which does eventually drain into Georgian Bay. And tracking the phosphorus inputs from these different land use types shows that more phosphorus was entering the bay from upstream sources than they previously thought. They thought that way more phosphorus was staying within the sediments and staying within the lakes before getting into Georgian Bay. And the chart on the right breaks down the phosphorus inputs into Georgian Bay. So 45% from forests, 23% wetlands, 14% from agriculture, 9% from septic tanks, and then 3% each from wastewater treatment plants, urban centers, and from Lake Simcoe. In this study, they did an interesting comparison of high impact versus low impact agriculture, high impact being monocultures and cropland, low impact being more hay and pasture. And they compared how these types of practices can have an effect on how much phosphorus is leaving the cultivated land. So high intensity agricultural phosphorus input was about 300% more than natural, but low intensity was only about 30% more than natural sources. And they also noticed that in rainier years, phosphorus input was higher since it's directly related to precipitation. And now noticing that relatively large red area between Barrie and Georgian Bay, that's the menacing wetlands, which we'll zoom into now. Menacing wetlands. Traditionally, wetlands have been seen as nature's kidneys, filtering out pollutants and having the ability to hold onto particulate phosphorus when it binds onto the sediments. And the menacing wetlands are the largest inland wetland in southern Ontario. What's been happening is that the land use changes to more agricultural areas are increasing erosion and increasing the total suspended solids into the menacing wetland. Since phosphorus has an association with sediments, this means that phosphorus is ultimately being loaded into the wetland. However, increased warming due to climate change and anthropogenic influence causes the conditions to be more warm and anoxic than usual. In low oxygen conditions, particulate phosphorus is actually mobilized and becoming soluble, going into the water of the menacing wetland. And we can see this in the graph here, that at lower dissolved oxygen content, basically anoxic conditions, total phosphorus becomes high. And so what they're finding is that the menacing wetlands are actually becoming a source of phosphorus for Georgian Bay rather than a phosphorus sink. Another anthropogenic source of phosphorus is the groundwater, namely the septic beds that are leaching phosphorus into the groundwater. And after agriculture, septic beds were seen as the second most important anthropogenic input. And the ideal situation is that the phosphorus from the septic systems becomes associated with the sediments, basically locked in there, but it seems that they're not trapped there forever. A group studied the septic beds in the Wasaga Beach area. In the 1980s to the 2000s, the septic beds were converted to city systems, putting the septic beds out of commission. Even though it's been years, some of them over 30 years since they've last been active, they're still shown to have a slow and steady effect. So this chart, our image on the left here, shows phosphorus plumes. Comfort Station 5 was decommissioned over 30 years ago and still has a noticeable effect. Comfort Station 6 below it also has an effect. It's worth noting that the groundwater percolates through an unconfined sandy aquifer that has a clay aquitard beneath. Now looking on a more larger scale at multiple septic bed plumes. This image on the right shows how the plumes are moving towards the water. The bay is on the left, and these plumes are described as, and I quote, slow-moving slugs making their way to the bay. They're so slow that not all of them will have an effect at the same time. Some will reach the bay and then they'll eventually end, and then others will reach the bay. While the measured levels are not likely going to affect the entire bay, they can certainly have nearshore effects on the shallow waters. And so this shows that it has a slow and steady effect on the bay over time, and since most of them haven't even made it there yet, that if their effects haven't even been seen. Our last anthropogenic influence in Georgian Bay that we're going to discuss is the invasive dry-scented mussel species, specifically zebra mussels, which we'll talk about Georgian Bay. They're filter feeders, clearing the water column and consuming algae. The phosphorus they ingest is essentially locked into their shells, living and dead, forming a phosphorus sink, and you can see this in the phosphorus cycle here along the bottom. But it's a complex system. They're also able to excrete soluble phosphorus, making it available for algae growth, showing that there's a lot of things interacting in the system, not just making it a simple pattern. And this is what I mentioned on the previous slide, the nearshore phosphorus shunt. Mussels are also able to excrete phosphorus, providing attachment for algae, increase in the photic zone because they're clearing the water, and they're making phosphorus soluble. So they're creating the perfect conditions for filamentous algae to come back, and they are slowly starting to see it come back in the Great Lakes. So it shows that there might need to be some new rules and regulations made. And it just shows that it's a very complex system. And now looking towards the future, we can see a couple of trends that might be happening. If we keep increasing agriculture to the north, there's going to be an increased effect of erosion on the bay, increasing phosphorus loading. As global warming and climate change happens, the phosphorus that is in the sediment, in the menacing wetlands, and other wetlands can be mobilized and increasing the soluble phosphorus in the water. Invasive species can cause an increase in filamentous algae and other types of algae, perhaps causing more events of cultural eutrophication. And another interesting thing to note is that when it gets warmer and there's less time for ice cover, the erosion becomes more significant. So the phosphorus inputs in Georgian Bay is a complex system. The whole thing is a complex ecosystem with a lot of different biotic and abiotic interactions that can't easily be predicted. We do know that land use changes directly increases total phosphorus inputs into Georgian Bay. And what happens in the water of Georgian Bay starts in the watersheds on the land. As the climate continues to warm, will more phosphorus be loaded into Georgian Bay, reversing effects that the menacing wetlands has had? And we do know that the efforts to reduce phosphorus loads into the Great Lakes has worked in the past. So we can continue to study and try to understand better how the land and water ecosystems interact. And finally, we can choose to protect land and have limited land conversion to agriculture to minimize our impact and to protect the environment.